All right, welcome. We're going to continue our discussion of the hydrogen electron. We're going to finish up with our discussion where we treat it classically with the Bohr model. Then we're going to continue on to talk about how an electron can also behave like a wave, and we're going to treat it quantum mechanically. So by the end of today, what we're going to be able to do is talk about how the hydrogen electron exists in a what we call a 1s orbital. And we're going to talk about all the different types of orbitals that the electron can exist in. We're going to go from that cloud to now thinking of these like more concrete shapes of where you can find that electron. And it all just comes down to the wave-like nature of our electron. Okay? And so in last class, we discussed how we can utilize the Bohr model, which treats electrons classically as particles, to explain the emission spectrum that we saw. Because we saw no matter how we looked at our hydrogen electron, whether it was using the diffractor that turned into the separate waves or our ocean spectrometer, we saw that that the hydrogen would have these lines at specific wavelengths. And the reason we get these specific wavelengths, these what we would call discrete energies of photons, is because the electron is moving between discrete energy levels. It's not going between a continuum of possible energy levels. There are a few allowable values. And we called those allowable values orbits. And these orbits are around the nucleus at a fixed radii, so a fixed distance away. And once we make this stipulation that we have these fixed radii, then we can say that an electron can move between any two fixed radii, and the difference in energy between them is what gives rise to any of these lines in the emission spectrum. And you can think of these fixed radii like an orbit around the sun by planets. And as we mentioned before, they're fixed because we need to have that specified difference in energy. And we designate them by the letter n. And a key thing we saw here was that we treat each orbit as, fixed energy coming from above, and these are what we call stationary states. And one of the key things we said here is that the lowest energy your electron can be is at the n equals 1 state. Let me find where it is, it cannot and does not spiral into the nucleus. Because if it did, then what we would see is we'd see a lot of release of energy as it continues to spiral down and down, and you get a more continuous spectrum. It would also, by definition, make the atom unstable. Okay? And so we have our lowest possible energy state, which is away from the nucleus. And if you want to imagine this, we can just, from the classical perspective, you can just think about how our planets are not spiraling into the sun. They're moving fast enough that the gravitational pull is counteracted by how fast they're moving, so that at any given time they're not spiraling into your nucleus. Okay? And then the last thing we mentioned was the energy of these fixed orbits. And we saw that, as you move between these different energy levels, you can have the emission of electrons. And we also discussed how if we do the opposite transition, so instead of going from 2 to 1, we go from 1 to 2, we would see an absorption of light at 657 nanometers, and we'd see a hole in our absorption spectrum. Okay? So we went ahead and we gave our equation for the energy levels of those orbits. We said that it's some constant, negative 2.18 times 10 to the negative 18th joules, times 1 over n squared, where n is your orbit level or your orbit energy level. Okay? And I've given you 4 of those energies for n equals 1, 2, 3, and 4. We said our difference in energy is just given by taking, this equation for your first n value and then the same equation for your second n value, subtracting from each other. So you could pick any two of these 4 energy levels we see here, subtract them from each other. You could get a difference in energy. But if you don't want to calculate each one of these individually and then do the subtraction, you can also group terms when taking E final minus E initial, and you can end up with this expression here, where we have 1 over n final squared over 1 minus n initial squared. And so as we're moving between these energy levels, what we're doing is we're either absorbing a photon as we go up in energy, or we're emitting one as we go down in energy. And the energy of that photon, which is given by h times frequency, or h times the speed of light divided by the wavelength, this is always positive. And in order to maintain that, we have a relationship that the energy of the photon released or absorbed is always the same magnitude as the change in energy of the hydrogen electron, because the hydrogen electron is either gaining energy from the photon or it's losing energy as a photon. But there is a sign convention we have to follow. We have to make sure that E photon is always positive, and so we're going to see that sometimes it's the positive version of delta E for the electron, sometimes it's negative, but it is always going to be the absolute value of the change in energy for the electron. Okay? For emission, we see that the sign is negative here. So we have to take a negative of the change in energy of the electron, and that's because the electron itself is moving to a lower energy, more stable state, meaning that it has a decrease in its energy, which is going to be a negative number. So we have to do a negative, we have to say that E photon is equal to negative of a negative number in order to make that positive. For absorption, we see that the E photon is equal to exactly E electron, and that's because this E electron, this delta E electron, the electron is moving to a higher energy excited state, meaning it has gained energy, and that gained energy means that it has a positive change in energy. And so we just have to make sure we're following that sign convention, okay? We then did a problem together where we talked about a hydrogen electron transition, and we were looking as it goes from n equals 2 to n equals 1. And so this n equals 2 is the initial state, this n equals 1 is the final state, and that's probably the most important thing we can do is label where we started and where we finished. Because after that, we just have to plug it into our equation here. So if we do that, we have our constant negative 2.18 times by 1 over n final squared, which is 1 squared, minus 1 over n initial squared, which is 2 squared. And we do that calculation, we'd see that this half of this is negative 1.64 times 10 to the negative 18th joules. Okay? And what we did in class is we started by saying the energy of the photon is equal to the negative delta E for the electron, because this in and of itself is a emission. You have had a hydrogen electron move from an excited state, or a larger value orbit, to a lower energy state, in this case the ground state, which has a smaller value of that n term. And so the energy of the photon, we take a minus of the minus to turn that into a plus. We get 1.64 times 10 to the negative 18th. But like we said on the last slide, for the energy of the photon, you can always say that's the absolute value of the change in energy for your electron. Okay? We then determine the wavelength for this by taking the energy we have, setting it equal to Planck's constant times the speed of light divided by wavelength. We're trying to solve for wavelength, so we're going to switch these two with each other. We get wavelength is equal to hc over E photon. We solve that. We see that's 121 nanometers, or 1.21 times 10 to the negative 7th meters. This is in the UV range, which makes sense since we've moved down to the n equals 1 energy level or orbit. Okay. So now let's try with a couple different numbers here. So I want you to pause the video here and work through each one of these. So I want you to find out what is the energy and what is the wavelength for each of these transitions. And I just want you to state where does that sit on the electromagnetic spectrum. All right? Okay, so pause. And I assume you have come back from the pausing. And so let's kind of go through and work this. So as we did on that previous slide, we're going to write down our n final and our n initial. And I'll say that my n final is 5 and my n initial is 2. It's because we started from 2 and we went to 5. Okay? So now we can just plug that into our equation. We'd have that delta E for your electron is equal to negative 2.18 times 10 to the negative 18th joules, multiply to 1 over n final, which is 5, squared, minus 1 over n initial, which is 2, squared, and we can go ahead and evaluate that. We'd see this is negative 2.18 times 10 to the negative 18th joules, 1/25 minus 1/4, and as we do that math, we'd get that this is equal to 4.578 times 10 to the negative 19th joules. Okay? And when we're looking at this, we're going to assume that, N2 and N5 are exact numbers. So we're going to base our sig figs based off of how many we have in our constant here. So we're going to say 3 sig figs, 7 Cs, and 8, so it rounds up. So we'd say that the delta E for the electron is equal to 4.58 times 10 to the minus 19th joules. In this case, we're going to say that because this is an absorption, E photon is equal to plus delta E for the electron. So let's just say EP is equal to plus delta E electron, which is equal to that 4.58 times 10 to the minus 19th joules. And then like we did on the other slide, we can say that our wavelength is just equal to HC over EP, which would be, and I'll switch colors here, 6.626 times 10 to the minus 34 joules dot second times the speed of light, which is 3.00 times 10 to the 8th meters per second, divided by the energy of the photon, 4.58 times 10 to the minus 19th joules. Joules is going to cancel with joules, per second cancels with per second, and you'd get that this wavelength is equal to 4.34 times 10 to the minus 7th meters, which is the same as 434 nanometers, which puts this in the visible range, and it's going to be purple. Okay, so let's also look at the transition for 7 to 3. We'll do this in red, and for 7 to 3, 7 is our n initial, 3 is our n final. So we say that delta E for the electron is equal to negative 2.18 times 10 to the negative 18th joules multiplied by 1 over 3 squared minus 1 over 7 squared. I'll spare you showing all that math again. We'd get that this delta E is equal to, excuse me, negative 1.977 times 10 to the minus 19th joules, 3 sig figs once again, 7C7. So delta E electron is equal to negative 1.98 times 10 to the minus 19th joules. And in this case, this was, because this is negative, the electron has relaxed. It's gone from a high energy state to a lower energy state. So we're going to say that the E for the photon is equal to negative delta E for the electron. And I'll just write that this was emission and that the former one was absorption. Okay. So that means that our EP is equal to plus 1.98 times 10 to the minus 19th joules. Wavelength is equal to HC over EP, so 6.626 times 10 to the minus 34th joules multiplied by seconds times the speed of light, 3.00 times 10 to the 8th meters per second divided by the energy of the photon plus 1.98 times 10 to the minus 19th joules. And then we can cancel our like terms, joules with joules, per second with per second. And when we evaluate this, we'd see that that wavelength is equal to 1.01 times 10 to the minus 6th nanometers, sorry, not nanometers, 10 to the minus 6 meters, which is the same as 10, 10 nanometers, putting this in the infrared zone, or the IR. So I'll write that out as infrared. Okay, so we'd have that. And one thing I will say is that for the sake of brevity, I did this rounding. I did the rounding of the delta E's at this point, right here and right here. And that's good if we're reporting the delta E for the electron. But for completion, what we should do is use the whole value when we do our division to find out our wavelength. And so what we should have here is instead 4.578 times 10 to the minus 19th joules. And then here we should do 1.977. So 1.977 times 10 to the minus 19th joules. And that's just so that we don't have excessive rounding errors impact us. Okay, so let's just summarize what we have here, and then we'll be able to break into treating our electron quantum mechanically. So we can summarize what we've seen so far about the Bohr model. We said that the Bohr model allows electrons to exist in discrete energy levels described by a quantum number, or described by a value n that was either 1, 2, 3, 4, etc. It was never n equals 0. Our lowest energy state was n equals 1. And we said that the energy involved in the transition from different energy levels is involved, and it is going to come from photons being absorbed or emitted when we're looking at absorption and emission spectrum. And the absorption doesn't only have to come from photons. We saw that we can run a current through them, and we can also excite electrons that way. But when we're looking at specifically photons, we see that those absorptions and emissions reflected in the respective spectra, where we see we have holes in absorption spectrum where energy has been absorbed, and then we have our lines in emission spectrum for where energy is being released as electrons relax back down. Okay. There is some limitations, though, to the Bohr model, and it only applies to the hydrogen atom. And that's simply because other atoms have more electrons. Or really, they just have more than one electron, and that really complicates things. Okay. Second limitation is that classical physics, the electron just as a particle, dictates that the electron should fall into the nucleus, assuming it's not zooming super duper fast. And the Bohr model kind of just didn't give a reason for why the electron wasn't spiraling into the nucleus. It was just that in order for everything to work, we had to assume that the electron wouldn't spin into the nucleus. So we don't have a reason. We just had to assume. Previously, had to just assume without any reason for why. Had to assume. And these circular orbits still describe electrons solely like a particle, which, is fine for a majority of phenomena. But just like we saw for light, sometimes you have to look at things quantum mechanically to explain all the properties of that thing. And, what we're going to have to do in order to combat, this part right here, as well as this part right here, is we're going to have to treat the electron as more than just a particle. We're going to have to treat it like a wave. And so in the next video, we're going to talk about how we can treat the electron like a wave and how that helps us to understand the hydrogen atom itself.